Welcome to this coding walkthrough. Today, we'll be tackling a fascinating problem called count collisions on a road. In this problem, we'll explore how to simulate interactions based on car directions and calculate the total number of collisions that occur. Let's dive in and break it down step by step. In this problem, we are tasked with analyzing a one-lane road where cars can either move to the left, move to the right, or remain stationary. The input is a string called directions, where each character represents the state of a car. Specifically, L indicates a car moving left, R indicates a car moving right, and S represents a stationary car. As cars move along this road, collisions can occur. If two moving cars collide, both cars become stationary. Similarly, if a moving car hits a stationary car, it also becomes stationary. Our goal is to calculate the total number of such collisions on the road. The input string can be as long as 100,000 characters, so we need to find an efficient way to solve this problem. The output will be an integer representing the total number of collisions that happen on the road. Let's consider some examples to better understand the problem. In the first example, the input string directions is RLRSLL. The first collision occurs when the R car moving right collides with the L car moving left, causing both to become stationary. This updates the string to SSRSLL. Next, the second R collides with the stationary S, becoming stationary itself. The string now becomes SSSSLL. Finally, the two L cars collide with the stationary cars, contributing additional collisions. In total, there are 5 collisions. This demonstrates how we track each interaction along the road to count the total number of collisions. Now, let's look at another example. Here, the input string directions is LLRR. In this case, no collisions occur because all the L cars are traveling leftward, and all the R cars are traveling rightward. Since there's no interaction between the cars, the total number of collisions is 0. This shows that the direction of movement plays a critical role in determining whether or not collisions occur. If cars are moving in opposite directions but don't cross paths, the result will remain collision-free. Finally, let's consider some edge cases to ensure our solution handles all scenarios. If the input string contains only a single character, such as R or L, no collisions are possible, and the output is 0. Similarly, if all cars are moving in the same direction, like RRRR or LLLL, there will be no collisions. For alternating patterns like RLRLRL, multiple collisions can occur depending on the sequence. If all cars are stationary, such as SSSS, no collisions happen either. Lastly, the problem can include large inputs, such as a string with 50,000 R cars followed by 50,000 stationary cars. In such cases, the solution must be efficient and handle the upper limits of the constraints without performance issues. To begin solving this problem, we can consider a brute force approach. The intuition here is to simulate the behavior of the cars as described in the problem statement. Starting with the leftmost car, we process each collision one step at a time. For example, if a right-moving car, represented by R, collides with a left-moving car, L, the result is a stationary car, S. We continue this process, iterating through the string and updating the state of the cars involved in each collision, until no further collisions occur. While this approach is straightforward and easy to implement, there are a couple of key observations to note. A car moving to the right can only collide with a stationary car or a left-moving car ahead of it. Similarly, a left-moving car can collide with a stationary car or a right-moving car behind it. However, the trade-off is that this approach has a time complexity of O(n)² because we repeatedly scan and modify the string. This makes it inefficient for larger inputs. Now, we turn our attention to a more efficient solution. Instead of simulating each individual collision, we can calculate the total number of collisions directly by analyzing patterns in the string. Here are some key observations that make this possible. A right-moving car, R, will eventually stop if it encounters a stationary car, S, or a left-moving car, L, ahead of it. Conversely, a left-moving car, L, will stop if there is a stationary car or a right-moving car behind it. This means that any non-stationary car, either R or L, that ends up colliding contributes to the total collision count. With these insights, the implementation becomes straightforward. We can remove any leading left-moving cars and trailing right-moving cars since they will never collide with other cars. After this, the remaining R and L characters in the string represent all the cars that will eventually collide. This approach is highly efficient, requiring only a single pass through the string, resulting in a time complexity of O(n). While there is an alternative method using a stack to dynamically simulate collisions, it adds complexity without offering significant performance benefits compared to this optimized solution. Given these considerations, the optimized approach emerges as the best strategy. It combines simplicity with efficiency, allowing us to directly count collisions in O(n) time. While the brute force approach is intuitive and easy to grasp, it becomes impractical for large inputs due to its O(n)² complexity. On the other hand, the stack-based alternative, while feasible, introduces unnecessary complexity without improving performance. By leveraging the inherent patterns in the problem, the optimized solution provides a clean and effective method to calculate collisions without the overhead of simulating each interaction. This makes it the ideal choice for solving the problem efficiently and elegantly. The problem at hand involves simulating the movement of cars along a one-dimensional road. Each car is represented by either L, meaning it moves left, or R, meaning it moves right. Collisions occur when these cars meet head-on, and depending on the rules, cars may stop, change direction, or disappear entirely. Our objective is to figure out the final state of the road after all possible collisions have been resolved. To achieve this, the algorithm first parses the input, which is given as a string, where each character represents a car or an empty space, denoted by dot. By understanding the key properties of the problem, specifically, that L and R cars move in opposite directions and interact upon collisions, we can begin designing a solution that iteratively resolves these interactions until the final state is reached. Once the input has been parsed, the next step is to simulate the movement of cars along the road. To do this effectively, we initialize a data structure, such as a queue or stack, to keep track of the positions and directions of cars. As we iterate through the road string, we identify sequences where cars are moving toward each other. For example, we track the positions of our cars moving to the right and L cars moving to the left. With this setup, we then proceed to resolve collisions. When an R car encounters an L car, we calculate the collision point based on their positions and apply the predefined rules. If both cars disappear, the collision point is marked as empty. If one car stops, it becomes stationary, and if one continues moving, its position and direction are updated accordingly. After resolving all collisions for this iteration, we update the road string to reflect the changes and repeat the process until no further collisions are possible. After iteratively resolving collisions, the final step is to return the resulting state of the road. This involves converting the updated road representation back into a string format, which serves as the output. Now, there are a few key insights that are critical to solving this problem effectively. First, understanding the rules for resolving collisions is paramount. For instance, when equal and opposite cars meet, both disappear, but if one is stationary, it can halt the other. Second, the iterative nature of the simulation is important, as each collision impacts the state of subsequent cars. A single pass won't suffice unless advanced data structures are employed. Third, efficiently tracking the direction of cars is crucial for determining potential collisions and updating states in an optimized manner. To implement this solution, we rely on specific data structures. A queue or stack is particularly useful for tracking the positions and directions of cars, as they allow efficient access and updates during the simulation. Additionally, the road can be represented as either a string or an array. Using an array enables in-place updates, which can reduce memory overhead. In terms of complexity, the time complexity of this algorithm is O(n) per iteration, where n is the length of the road. However, in the worst case, resolving collisions may require up to O(n) iterations, leading to an overall time complexity of O(n²). The space complexity is O(n), as we need to store information about the cars and their positions in the data structures. When solving this problem, it's important to consider several edge cases. For instance, if there are no cars on the road, the output will simply be the same as the input. Similarly, if all cars are moving in the same direction, no collisions occur, and the road remains unchanged. On the other hand, alternating sequences of L and R cars require careful handling, as multiple collisions may need to be resolved iteratively. Let's look at an example to solidify these concepts. Given the input R, GL, we first parse it to identify an R car at index 0 and an L car at index 4. As these cars move toward each other, they eventually meet in the middle. According to the rules, both cars disappear upon collision, leaving the final state as. Hence, the output for this input is. This solution efficiently calculates the number of collisions on the road by analyzing the string of car directions. First, we initialize the collision counter and determine the bounds of the relevant section of the road where collisions can occur. Any L cars at the start and R cars at the end are ignored since they cannot collide based on their direction. Next, we iterate through the remaining portion of the string, counting every car that is not stationary, S. These R and L cars contribute to collisions. The final count is returned, representing the total number of collisions. This method avoids unnecessary computation and runs in O(n) time, where n is the length of the input string. This is the Java implementation of LeetCode problem number 2211, count collisions on a road. The logic mirrors the Python solution, which calculates the number of collisions by skipping L cars at the beginning and R cars at the end, as they cannot collide. The remaining cars in the range are checked, and each R or L car contributes to a collision. The implementation uses Java-specific constructs like char for string manipulation and follows Java conventions for loops and type declarations. To solve this problem, we start with the input string RLRSLL, which represents the directions of cars on the road. First, we initialize some variables. Collisions is set to 0 to keep track of the total number of collisions, n is the length of the input string, left is initialized to 0 to begin at the start of the string, and right is initialized to 5, the last index in the string. Next, we check for any L cars at the beginning of the road. Since the first car, directions, 0, is R, no skipping occurs, and left remains at 0. Similarly, we check for any R cars at the end of the road. The last car in the string, directions, 5, is L, so again, no skipping occurs, and right remains at 5. Now, we move on to count collisions in the middle of the string by looping through the range from left to right. At index 0, the car is R, which causes a collision, so we increment collisions to 1. At index 1, the car is L, which also causes a collision, increasing collisions to 2. At index 2, the car is R, and we add another collision, making the total 3. At index 3, the car is stationary, represented by S, so no collision occurs, and collisions remains 3. At index 4, the car is L, causing another collision, bringing collisions to 4, and at index 5, the final L car causes one more collision, resulting in a final count of 5. The output for this example is therefore 5. Let's look at a new example with the input SSRL. We begin by initializing our variables. Collisions is set to 0, n is 4 since the input string has 4 characters, left starts at 0, and right starts at 3, the last index of the string. We then check for any L cars at the start. The first car, directions, 0, is S, so no skipping occurs, and left remains 0. Similarly, we check for R cars at the end of the string. The last car, directions, 3, is L, so no skipping occurs here either, and right remains 3. In this step, we count collisions in the middle of the string by iterating from left to right. At index 0, the car is stationary, represented by S, so no collision occurs, and collisions remains 0. At index 1, the car is also S, so again, no collision occurs, and collisions remains 0. At index 2, the car is R, which causes a collision, so we increment collisions to 1. Finally, at index 3, the car is L, which also causes a collision, bringing collisions to 2. The output for this example is 2. Now, consider the input LLRSR. First, we initialize the variables. Collisions is 0, n is 5 since the string has 5 characters, left starts at 0, and right starts at 4. Next, we skip any L cars at the start. The car at index 0 is L, so we increment left to 1. The car at index 1 is also L, so we increment left again to 2. At index 2, the car is R, so we stop skipping, and left remains 2. Then, we check for R cars at the end. The car at index 4 is R, so we decrement right to 3. At index 3, the car is stationary, represented by S, so we stop skipping, and right remains 3. Finally, we count collisions in the middle of the string by iterating from left to right. At index 2, the car is R, which causes a collision, so we increment collisions to 1. At index 3, the car is stationary, represented by S, so no collision occurs, and collisions remains 1. The output for this example is 1. To analyze the time complexity of the solution, we start by breaking it down into its individual steps. First, the initialization step, where variables like collisions and n are set up, takes constant time, or O1. Then, we have the task of skipping over the L cars at the beginning of the string. This is done using a while loop, which continues until the first non-L character is found. In the worst case, if the entire string is made up of L characters, this loop iterates through all n characters, making it an O(n) operation. Next, there's a similar step for skipping our cars at the end of the string. Again, this involves a while loop that processes the ending segment, and if all cars are R, the operation also takes O(n) in the worst case. Finally, we have the step where collisions are counted in the middle section of the string. Here, a for loop iterates through the characters between the left and right pointers. At most, this covers the entire string, with each character being checked in constant time. This makes the collision counting step another O(n) operation. When we combine all these steps, we see that the overall time complexity in the worst case is the sum of O(n) for skipping L, O(n) for skipping R, and O(n) for counting collisions, which simplifies to O(n). Now, turning to space complexity, the solution is highly efficient as it only uses a constant amount of extra space. Variables like collisions, left, right, and n require O(1) space, and there are no additional data structures, such as arrays or stacks, that grow with the size of the input. The input string directions is treated as read-only and does not contribute to extra space. To compare this with a brute force approach, a less efficient method would involve simulating the movement of cars step by step, checking for collisions at each step. This would require multiple passes over the string, leading to a time complexity of O(n) squared, and potentially additional space for intermediate states, resulting in O(n) space complexity. By focusing only on the relevant segments of the string, the provided solution avoids unnecessary work and achieves O(n) time complexity and O(1) space complexity, making it far more optimal. Now, let's consider the best, average, and worst-case scenarios for this solution. In the best case, if all cars are either L moving left or R moving right, the while loops will process the entire string, but the for loop will not execute since there are no middle characters to check. This results in a total complexity of O(n). In the average case, where the string has a mix of L, R, and S characters, the while loops and the for loop will both process the string once, leading to O(n) time complexity. In the worst case, if all cars are stationary, S, the while loops will skip no characters, and the for loop will iterate through the entire string, again resulting in O(n) complexity. Mathematically, this is supported by the fact that the while loops together process subsets of L and R characters, with at most O(n) iterations. Similarly, the for loop processes each remaining character exactly once, with O(1) operations per character. Adding these contributions gives a total time complexity of O(n). This is optimal because the input string must be scanned at least once to determine collisions, and O(n) is the theoretical lower bound for such problems. When working on this problem, there are several common mistakes to watch out for. First, ignoring edge cases can lead to runtime errors or incorrect results. For example, consider scenarios like an empty input, a single car, or strings where no collisions occur because all cars are moving in one direction. Testing for these cases explicitly is critical. Next, be cautious about the order in which collisions are handled. Resolving collisions from right to left instead of left to right, or vice versa, can disrupt the logical flow and lead to incorrect answers. Another pitfall is relying on an inefficient brute force solution. Simulating every collision step by step, especially for large inputs, can drastically increase time complexity. Instead, look for ways to reduce unnecessary computations. Additionally, avoid hard-coding your solution for a fixed input size, such as assuming the maximum length is always 10 to the power of 4. Solutions should dynamically handle varying input sizes to ensure robustness. Finally, overcomplicating the problem by introducing extra data structures or over-engineered steps can make your code harder to understand and debug. A simpler, more straightforward approach is often both more efficient and easier to communicate in an interview setting. Now, let's look at some interview-specific insights. A key strategy is to focus on recognizing patterns in collisions, such as identifying when two cars moving in opposite directions will inevitably collide. Efficient solutions often hinge on accurately processing these interactions. For optimization, consider using a stack-based approach. This can significantly reduce time complexity compared to brute force methods by simulating only necessary collisions. During interviews, it's important to communicate your thought process clearly. Explain why you've chosen a particular method, the order in which collisions are being processed, and why you selected a specific data structure. This clarity helps interviewers understand your reasoning. Additionally, don't hesitate to ask clarifying questions. For instance, you could confirm how simultaneous collisions should be handled or ask about any constraints like maximum input size. These questions demonstrate that you're thinking critically about the problem. There are also related problems that can help strengthen your understanding of collision-based scenarios. For example, LeetCode 735, Asteroid Collision, involves a similar concept where objects interact based on size and direction. LeetCode 71, Simplify Path, is another useful problem that focuses on stack processing, which can help you practice stack-based approaches. LeetCode 856, Score of Parentheses, is yet another stack-related problem that emphasizes processing sequential relationships. Finally, LeetCode 42, Trapping Rainwater, is valuable for improving your ability to recognize patterns in sequential interactions, which is a key skill for solving collision-type problems effectively. By practicing these related problems, you can build a solid foundation for tackling variations of this problem. Let's discuss some alternative approaches for solving this problem. One effective method is using an optimized stack simulation. In this approach, you use a stack to track cars moving in one direction, resolving collisions as soon as a car moving in the opposite direction is encountered. This reduces the time complexity to O(n). However, the trade-off is that it requires additional space for the stack, although the runtime gains often outweigh this cost. Another option is the two-pointer approach, which simulates interactions between cars by moving pointers from opposite ends. While this can be effective under certain constraints, it may not be as intuitive as the stack approach and avoids additional space usage. Finally, there's the brute force approach, which directly simulates every interaction step by step. While this method is simple to implement and easy to understand, it comes with a time complexity of O(n squared, making it impractical for larger datasets. Choosing the right approach depends on the constraints of the problem and your familiarity with these techniques. Great job following along. We've summarized the key points of the problem and its solution. Remember, practice makes perfect. Keep challenging yourself with similar problems. Thank you for watching, and don't forget to like and subscribe for more content like this. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!